Welcome to Chapter 3 in Math 95. This is Gary Parker. Good day to you. So Chapter 3 is all about radical expressions, equations, and functions. It's really important, radicals are square roots, in working with a lot of other functions too. So all the stuff we do in Chapter 3 is going to be super important when we move on to Chapter 4. That's stuff about quadratics, and I'll mention that in just a moment. Chapter 3 and Chapter 4 are going to be combined together into your Unit 2 exam. This one's a wee bit harder than the first exam, so you want to definitely start on that practice exam early once you're into Chapter 4. So, quick overview of this chapter. Radicals are roots of a kind, and roots are all related to powers. If I can get my magic pen. All right, so we've got roots versus powers. So related to the idea of squaring something, like we know that 2 squared is 4, is the idea of a root. So the square root of 4 equals 2. Similarly, if I were to take 2 and cube it, I would get 8. So there's a cube root. Now, a cube root, you make the square root symbol, but you put a little 3 right there. And that indicates you want to find a number that you write down 3 times to multiply to get the number in the box. So I know that 2 times 2 times 2 is 8. So the cube root of 8 has to be 2. We could take 3, raise that to the 4th power. 3 times 3 is 9. Another 3 times 3 is 9. 9 times 9 is 81. So that means the 4th root of 81 has to be 3. So mostly we're going to be playing around with roots and again, mostly just the square root, although we will touch on other roots over here. So another important idea is this symbol right here. This symbol is called the principal square root. And it's got the name principal because it turns out there's another square root. And it's called the other square root. Whoa, what happened? All right, my magic pen's being freaky today. The other square root. You might ask, well, what the hell is the other square root? So I'll show you with an example. Suppose, for example, I said I squared a number and the answer was 4. Well, the obvious answer here is to say, well, you squared 2. However, it is true that 2 squared is 4, but it is also true that negative 2 squared, right, which means negative 2 times negative 2 is also 4. So negative 2 is the other square root of 4. This symbol right here wants the non-negative. So that's what we mean by principal. Non-negative. You may be saying, why doesn't he just say positive? We'll get to that. So we have a non-negative root and we have the other root. The other root is pretty much going to be the negative root. You may ask, what's the symbol for that other square root? Well, it's the opposite of the square root. So you got the principal square root and the opposite of the principal square root. So every number pretty much has 2 square roots. Now, sometimes that gets a little weird because square root of 0, well, that's 0. And the other square root of 0, well, order of operations here, a negative in front like that really means negative 1 times whatever comes next. Order of operations, there's a implied parentheses around this because of that symbol encasing it. So I have to take the square root of 0 first. The opposite of 0 is still 0. So 0 is the only number whose other square root is the same thing. Every other number has 2 square roots, sort of. Next special case. When we go to take the square root of a number, like say b, and we claim the answer is a, that's only true if we take a and square it. In other words, we take a times a, and we get that new number b. Okay? So for example, earlier we looked at the square root of 4, which we claim is 2. And that's true because 2 squared, which is 2 times 2, is 4. Okay, so here's where it gets a little interesting. What if you try to take the square root of a negative number? And you may ask, what is that answer? Well, for now, we're going to say it doesn't have an answer. However, we missed something back in history on that. So there's an answer here if we can find a number whose square, meaning we take that number and we multiply it by itself. So here I'm using question mark as a variable. And that's going to give me -1 back. But the numbers we're familiar with, if we take a positive times a positive, we get a positive. If we take a negative times a negative, we still get a positive. So we haven't come across any numbers yet for which the number times itself is negative. Turns out there is a kind of number that works for. They're called imaginary or complex numbers, and we'll get to that at the end of this chapter. So we need, but don't have yet, an idea called complex numbers. And complex numbers take into account that the square root of -1 is necessary for a lot of the science that we've discovered. So if you like your lights turning on and the way your toilet flushes, we can thank our knowledge of the square root of -1, believe it or not. Okay, so playing with square roots. So one thing about a square root is that when we take a square root of a number, like 4, we can all agree that the answer is 2. Square root of 9, we can all agree that the answer is 3. If we try to take something like square root of 2, 2 isn't a perfect square, so we got to do some work to do that. And these days, we just use a calculator. So let me whip out a calculator. I could use Desmos. And so I asked Desmos for the square root. The international abbreviation for square root is SQRT. Desmos changes that into the symbol for us, no parentheses necessary. And then I can type something like 2, and Desmos says the answer is about 1.414213562237. And this decimal goes on forever without repeating. But we have techniques for calculating the next place. If you're curious about that, ask me and I can demonstrate how to do that by hand, but it's kind of a pain in the butt. Calculators do it well for us. So we'll just say the square root of 2 is about 1.41. And every calculator is going to agree on that. So I'm going to put a wavy equals because I'm rounding 1.41. So what that means is since when we plug in a number, we get a single output or no output at all, that means this is a function. So the square root of x is a function. So that means I can write it as a function. F of x equals the square root of x. Now remember, f of x is just a y value, so that's the same thing as saying y equals the square root of x. And so let's take a look at the graph of this. So f of x equals the square root of x is what I want to look at the graph of. And I'm just going to calculate some numbers by hand, and then we'll whip it into Desmos. So I'm going to pick some x's, calculate the y's. So often, like with lines, I'll pick like -2, -1, 0, 1, and 2, and see what happens. However, if I try to take the square root of -1, -2 there, wrong spot, I'm going to have a problem because that leads me into complex numbers. And complex numbers exist in a different kind of way. So if I say, what's the square root of -2, Desmos? Desmos says, I'm sorry, that's undefined. I can't show that on this plane, on this grid. We need another dimension to show that. That's kind of hard to see and feel. I'll talk about that later. So for now, there's no answer. Oops. same thing here. There's no answer here either for now. Square root of 0, that's just 0. Square root of 1, that's just 1, because 1 times 1 is 1. Square root of 2 is about 1.4-ish. Square root of 3, let's skip that. Let's do one we can do in our head. Square root of 4 is 2. And let's skip to another easy one. Square root of, oops, like a 9. Square root of 9 is 3. So I'm just going to do a rough sketch of what this looks like. So here's my y-axis. Whoa, not very straight today. And my x-axis. And I want to get up to 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's throw 10 there. And then as far as y values go, I'm only going from 0 to 3. So 1, 2, 3. And when you make a graph by hand, you should always label it, showing which variable is where, and throw a few numbers down so somebody else can read it. And I'll plot these points now. So I've got the point 0, 0, 1, 1. 2 is about 1.4, so maybe about here-ish. Let's see, 1, 2, 3, 4. That gives me 2. So what about there, do you think? Graph paper would be really nice, wouldn't it? And 3, 9, somewhere over there. So notice that it's steeper over here than it is out here. So it gets shallower as we move out. So I'm going to attempt to connect the dots here. So it looks something like this. And I'm going to make an arrow to indicate it continues in this direction. As I pick bigger x values out this way, I'm going to get slightly bigger answers when I take the square root. Square root of 100 is 10, right? Square root of 400 is 20. But it's shallower as I move out. It's never going to get flat. It's always going to keep going up as I move right. So that's the square root function. If I were to graph the other square root, y equals the opposite of the square root of x, that would basically take the opposite of each of these y values. And so I would get a symmetric curve underneath here. So this down here is the graph of the negative square root of x. So the blue thing on its own is a function, the red thing on its own is a function, but together they wouldn't be, right? Because they failed the vertical line test. But individually they are. And notice they're mirror images of each other. And that makes what's called a sideways parabola. We'll talk about parabolas more in the next chapter. So in section 1, you're going to learn more about the square root function. So I'll just show a few of them here. Let's go to Desmos. So I'm going to call this one f of x equals the sqrt, and then it whips out that symbol of x. Ooh, I didn't put equals there, did I? It's a minus. There we go. And then it graphs it for me. I don't want it to be red. I want it to be a different color. How do I get it to change color? Can I do that? I've sworn you can change colors on these guys. Oh well, we'll just go with it. Other square root functions. What if you put something else inside? Like what if I tried to graph the square root of x minus 5? Notice when I do a minus 5, it shifts the graph to the right. It's the same basic shape. Right over here, I had a point over 1, up 1. And from the starting point here, I have a point over 1, up 1. So it's the same shape. I just shifted it to the right. Just kind of weird, because minus 5, I thought that might go to the left. But what if I graph the square root of x plus 3? Ooh, that goes to the left. Same shape, but goes to the left. So in section 1, you're going to learn a bit about manipulating this shape. Okay, so I'm going to leave that there. Those are called transformations of a function. All right, back to some other important facts about square roots. Another cool thing about square roots is that they're related to powers. And I already mentioned that, but I'm going to go a little deeper on it. So consider the idea that squares and square roots are opposites of each other. So for example, if I take the square root of 2 squared, that's going to give me 2 back. The root and the square cancel each other. Okay? If I put a 3 in there, This will be a 3 back. Double check. 3 squared is 9. Square root of 9 is definitely 3, right? So it checks out. So the root and the power cancel, and it doesn't matter what order I do that in. So if I were to take the square root of 3 and, let's see, that what I want to do? Yeah, and square it, I'm still going to get 3 back. Okay, so let's double check that. Why? This means to take, squaring something means take the thing times itself. And my claim is that if you multiply 2 roots together, you can join them. So this is the same as the square root of 3 times the square root of 3, which is the square root of 9, which we all know to be 3. So the order that you apply the root or the square doesn't matter. So let's look at that another way. Suppose we take a 3 and we square it, and then we want to raise that to some other power, let's call it box, and we want the answer to be 3. What could happen there? Let's bring that up to a new screen. So I've got 3 squared to some other power. Power to a power, think way back to a previous course, you multiply them. So this is 3 to the power 2 times whatever box is. Now we want the answer to be 3. 3 is really 3 to the first. So what we can do here is we can isolate and say, well, that means this power has to be 1, because the bases are already the same. So I can whittle this down now to say, well, that means 2 times some number has to be 1. To solve for this missing number, we would divide both sides by 2. And we get that missing number has to be 1/2. Okay, let's put that back in and see if it makes sense. If we take 3 and raise it to the second power, and then raise that to the power 1/2, that's going to give us 3 to the power 2 times 1/2. Half of 2 is 1, so we get 3 to the first, which is 3. Okay, so the square and the power 1/2 cancel each other. Now, in the past, you haven't dealt with fractional powers probably, but they exist. And that fractional power behaves the same way as a square root. So this is an important rule. That another way to deal with the square root of x is to call it x to the power 1/2. Similarly, if you wanted to do, say, the cubed root of x, you could use x to the power 1/3. Now, on a lot of calculators, to type a root, or a power, you would use what's called the caret key on the keyboard. It's Shift-6 to get to that. And since the exponent is complicated, I have to put it in parentheses. So on a lot of calculators, I would have to type it this way, right there. So earlier, we looked at the cubed root of 8, and the answer is 2. So what I want you to do on a calculator is type 8 raised to the power 1/3 and see what you get. Computer better give us 3. So I'm going to go not to Desmos, but to my Google calculator. 2 plus 2 will bring me there. All right, so then I'm going to type 8, and then I'm going to use my x to the power button, and it jumps me up into the parentheses position, in the exponent position. Then I do my parentheses, 1 divided by 3 equals, and it says 2, which is just what I want. Now, on some calculators, when you go into the power position, you don't need parentheses, and in some you do. So at first, I always type the parentheses just to be safe, and then check, I wonder if my calculator could do it without the parentheses. Raised to the power, 1 divided by 3. Oh, crap, it pulled that 1 divide by 3 out of the power. So in the Google calculator, probably on most Android calculators, you have to use parentheses. Otherwise, it'll screw it up. Desmos, let's take a look. 8 raised to the power, so I'm going to go Shift-6, and that jumps me into the power position. And then I type 1/3, and Desmos kept the whole thing in the power position. Parentheses weren't necessary. It gave me 2. Typing parentheses won't hurt. Still get the same answer. Okay, so you got to learn how to use your calculator well. If you have any questions about your calculator, let me know. All right, a couple more things, and we'll call it a day. So that's just getting used to the square root. Excuse me. And a square root is the same as the 1/2 power. Cubed root is the same as the 1/3 power. You can read more about that in section, let's see, what section is that in? That is in section 2, new page. So just playing with square roots. So square roots, because they're exponents, have the same properties of exponents. So all the properties of exponents you learned before are going to be important. So if you have something like x times y raised to the power n, let me change the color on that. I don't feel like writing in red, if you don't mind. There we go. Oops, to change the pen. All right, that's equal to x to the n times y to the n. So a simple example of that would be to take 2 times 3 raised to the power 2. Exponent means write the base down twice in this case. So that gives me 2 times 3 times 2 times 3. Which multiplication you can write in any order you want. So I can choose to write that as 2 times 2 times 3 times 3, which is the same as 2 squared times 3 squared. Right? So that's just an arithmetic example about why that rule works up there. Another important rule is that if you take x divided by y, all to the power n, then that's going to give you x to the n over y to the n. Okay? So square root versions of these I'll put in red. So if I take the square root of something like 9 times 2, that's the same thing as the square root of 9 times the square root of 2. And hey, that's kind of cool. Square root of 9 cleans up. So this must be the same thing as 3 times the square root of 2. So you could check on a calculator. 9 times 2 is 18. The square root of 18 is the same thing as 3 times the square root of 2. So often we can use a rule like that to clean up, to pull perfect squares out of a square root and write it in its lowest term. So like you can reduce fractions, you can reduce square roots. That's an important part of sections 2 and 3. Over here, an example would be, say, how about the square control Z. Let's take out 9/2 and take the square root of that. So that would be the same according to this rule as the square root of 9 over the square root of 2. And you could stop here or notice, hey, 9's a perfect square. I could take that one more step. But this right here illustrates this property. That property is also useful in reverse. So new color. So if I started with something like the square root of 6 over the square root of 2, I can take this rule in reverse and say, hey, that's the same thing as the square root of 6 over 2. Well, that's kind of nice because 2 goes into 6 3 times, so that must be the square root of 3. So roots simplify a lot in certain cases. Important catch about the top rule and the bottom rule. So if I take the square root of x times y, that should be equal to the square root of x times the square root of y. Once I throw variables in there, it gets a little trickier because the principal square root can only handle at this point non-negative numbers. So this is only true, these things are only equal if x is greater than or equal to 0 and y is greater than or equal to 0. So you'll see notes like that in some of the problems. Assume all variables are non-negative. Otherwise, we can't apply this rule right here. It gets trickier because there's different cases. All right, what else fun do we have here? All right, one more thing, and I'm going to shut up for now. So you learned about an idea called like terms a while back in algebra. So for example, if somebody said add 3x and 2, well, boom, I did it. I can't clean that up anymore until I know what x is. I can add them, I just did. I can't simplify. So if things are like, they simplify further. If they're not like, they don't. So here they're not like, I don't. So compare that to taking 5x and adding that to 4x. So these guys have the same variable. So if you have 5x's and then you bring 4x's into the mix, altogether you have 9x's. So that's what I mean about like terms simplify. Like terms means you have the same variable and there could be more than one variable to the same powers. So for example, if I tried to add, say, 3x to 5x squared, I can't really simplify this anymore in terms of the addition because x squared is like a floor tile. X is like a measurement, maybe a piece of string. And what happens if you take 3 pieces of string and 5 floor tiles? You get 3 pieces of string and 5 floor tiles. There's not much more you can say about it. So different powers of the variables means they're non-like, means you can't take the addition any farther. Now, there may be other things you can do to this, like factor, but that's a different idea. So it turns out square roots have a similar property. So consider, for example, 3x plus 2 plus 4x. We know that the 3x and the 4x are like, so we can say this is the same as 7x. Actually, let's write that over here. Plus 2. Similar idea with roots would be having something like 3 times the square root of 5 plus 2 plus 4 times the square root of 5. Now, without a calculator, we can't do anything with the square root of 5 because it's not a perfect square. But if I have 3 square roots of 5, think that's an object you can possess. And then you have 4 of them over there. Altogether, you must have 7 square roots of 5. And then that 2 just kind of hangs on. And without a calculator, you can't take it any farther. Like up here, without x, you can't take it any farther. So like terms applies to roots also. Let me show you another kind of cool example. Consider the square root of 18 plus the square root of 2. At first glance, you'll say, damn, I can't simplify that anymore without a calculator because those are different roots. But we got a trick up our sleeves because we know that we can factor 18. I'm just going to do a little factor tree. 2 goes into 18 9 times, and 3 goes into 9 3 times. And cleaning up square roots, I like to use factor trees because then once I do the factor tree, I can say if I see 2 of a kind, it pops out as 1, right? Square root of 9 is 3. So that means the square root of 18 can be rewritten, let's go back to red, as 3, 2 of a kind pop out, times the square root of 2. I want to add that to 1 square root of 2. So altogether, I now have 4 square roots of 2. Now, this might be new and weird. You can always plug this into a calculator to double check. I'm going to do that right now in Desmos. So I want to see if 18 plus square root of 2, square root of 18 plus the square root of 2 is really the same as 4 square roots of 2. So Desmos, help me out here. Let's clear out a few things. All right, so first we started with the SQRT of 18. Arrow out of that, plus the SQRT of 2. Desmos says that's about 5.6568, blah, blah, blah. I believe, after my playing around, that's the same thing as 4 times the SQRT of 2. Oh, don't need parentheses here. And Desmos agrees they are exactly the same decimal value. Okay, so I can always check on a calculator. When I simplify a square root expression, does it come out, the answer match what I started with? So I got that going. All right. Oh, I lied. I got to show you one more thing. Typing things into our system here. Let's pick a homework problem. Not that one. Not that one. Let's look for a slightly easier one. No, I guess we'll do that one right there. Okay. Square root of 144 m to the 19th. Yeah, we can do that. All right, go back to my book here. So we're asked to clean up the square root of 144 m to the 19th. Now notice I always put this little hook at the end here. That's to be clear what's inside the root and what's not inside the root. So just an example, the square root of x plus 2 for we sloppy writers. Question, is the plus 2 inside the root or not? So what did I mean here? Did I mean the square root of x with the plus 2 on the outside, or did I mean the square root with x plus 2 on the inside? So I'm not the neatest writer some days, so I got in the habit of putting that little hook there to be clear what's inside the root and what's not. So if you're not a neat writer, it's a good recommendation. Can I go to the garbage, please? All right, so let's clean this sucker up. So a couple things to consider here. We have a property that square roots split on multiplication. So I can write that as the square root of 144 times the square root of m to the 19th. So you might recognize 144 as 12 squared. If not, you could make a factor tree on it. So if you recognized it, you could just jump straight to square root of 144 is 12. The root is gone in that part. Then I need to consider m to the 19th. If you didn't recognize that as the square root of 12, then what you would do is have to make a factor tree. So maybe whip out your calculator. 2 goes into 144 72 times. 2 goes into 72 36 times. 2 goes into 36 18 times. 2 goes into 18 9 times. And 3 goes into 9 3 times. And the principle for cleaning up square roots based on a factor tree is anytime you get a pair, it pops out as 1. So I'm going to get a 2 out there. I'm going to get another 2 out there. And I'm going to get a 3 out there. And what is 2 times 3? Well, it is 12. So there's more than one way to get this kind of problem done. Either a factor tree or you just recognize perfect squares. All right, next we got to deal with that m to the 19th. So again, I started with 144, m to the 19th. I now have that is the same as 12 times the square root of m to the 19th. And remember that the square root is the same thing as the power 1/2. Okay, well, that's kind of cool. So what I'm going to do is I'm going to rewrite this square root of m to the 19th as m to the 18th times m. So forget about the 12 for just a moment. And I can consider that to be the square root of m times the square root of 18, or m to the 18th. That's an m, believe it or not. And since the power is a 1/2, so that this right here is really the same as m to the 18th to the 1/2. So what that means is power to a power means multiply. So basically the square root cuts powers in half. So half of 18 is 9. So then this becomes, that square root of m is still chilling there. And the square root of 18 is, sorry, square root of m to the 18th is the same as m to the 9th power. Okay, because a power to a power means cut, right, that in half, or multiply, which cuts that in half. Now the 12 is still chilling out here the whole time waiting to be dealt with. Okay, so this is one way I could write it. Typically we write the square root last, so the usual way to write this would be 12 times m to the 9th power times the square root of m. And you're going to get to practice that. What I really wanted to get to is how the hell you type that into the computer. If you ever have trouble working here, when you click on one of these boxes, two things will happen. One, it'll give you a little message, enter an algebraic expression. Blow that sucker up. Actually, let's open this in a new window so we can see it better. And hopefully it doesn't give me a different problem. Which one was it? Not that one. Oh, darn, I lost track of it. Oh, 14. Ah, give me a different one. All right, that's okay. So I'm just going to claim I know the answer here. Oh, did I bump it to a new window? Darn it. All right, one more try. Open a new tab. Okay, now it's in a new window. So you shouldn't do this. I don't think you can actually in Canvas, but I can because I'm the teacher. All right, different problem yet again. I'm doing this just so video audience can see it better. So breaking this up, square root of 4 is 2. The x to the 9th can be rewritten as x times x to the 8th. And the square root of x to the 8th is going to be x raised to the 4th. And you can put a times in here or not. Without a symbol that means times, to type a square root in this system, you have to do SQRT, and the parentheses are absolutely necessary. In Desmos, they weren't. but here they are. In Android calculators, they are. Can't remember Apple calculators. I think square roots and Apple calculators are a pain in the butt. And then I'm going to be left with an x behind. And so it'll show me down below here what my answer is going to look like. And it says syntax OK, which means I typed it all right. Okay? It looks kind of weird there, but then it looks pretty there. I don't really need the times. I just like them in there, so it looks a little cleaner without. If you're having trouble typing stuff, you can hit the arrow button, and that brings up this editor here. And so then you can type stuff in here, like to x. If you're not sure how to do a power, just use the power button, and it drops it up there for you. So let's say I think I had x to the 4th power. Hit the arrow to get out of that. You have arrows here to help you move around too. And then we want a square root of x. And so I can get a pretty version of it here. And then when I save it, it types the proper way to do it here. And eventually you'll just get used to typing it yourself. But you always have that equation editor to help you out. So pay attention to a few things here. 1, use the equation editor if it seems complicated. 2, it'll give you a little hint on what kind of thing you're going to type. Are you typing a number? Are you typing an expression? Are you typing an equation? And then you can always hit more, and they'll give you some examples of the kinds of things you can type here. And then if it's a complicated thing, it'll tell you, did you type it OK? That doesn't mean the answer's right. It just means you typed something OK. For example, if I forget my parentheses, it should give me a little message that says, ooh, syntax error, unmatched parentheses. So pay attention to that stuff. And then you can submit it and hope it's right. Ooh, I got it right. Nice. All right, now your turn to play. Have a good day. Do good math. I'll catch you soon. Bye-bye.